Ground reflection Touré model. In our previous video lectures, we studied about the free space propagation model, which is majorly used for long distance communication and its received power calculations based on LOS. But in case of mobile or radio communication, there lies a single direct path between the base station and the device, and hence free space propagation model becomes inaccurate when it's used in this case. To prevent this problem, a model is introduced which is based on geometric optics and considered both direct and reflected paths between transmitter and receiver. This model is known as two-ray ground reflection model. Now let's talk about the theory. This model is found to be reasonably accurate for pretending the large-scale signal strengths over a distance of several kilometers. For mobile radio system that mainly uses tall towers, height exceeds from 50 meters, as well as for line of sight microcell channels in urban environments. We know that in case of mobile communication system, the maximum transmission receiving TR separation distance is at most only a few tens of kilometers. In this case, the earth can be assumed as flat. Now follow this diagram. Here, 2 points of transmission and receiving is present. Ht is the height of the transmitter, while the Hr is the height of the receiver. If E0 is the free space electric field at a distance of D0 from the transmitter, then for D is greater than D0, the free space propagating electric field is given by E of D, T, that is equal to E0 D0 by D multiplied by cos of omega c bracket under T minus D by C, where D is greater than D0. And also E of D, T is equal to E0 D0 by D represents the envelope of the E field at D meters from the transmitter. Now let's consider two propagating waves arrives at the receiver. The direct wave that travels a distance of D and reflected wave travels D double dash. The electric field due to the line of sight component at the receiver can be expressed as E of loss, that is D dash T is equal to E0 D0 by D dash multiplied by omega c bracket under T minus D dash by C. At the electric field for the ground reflected wave, which has the propagation distance of D double dash, can be expressed as Eg of D double dash T is equal to tau E0 D0 by D double dash multiplied by cos of omega c bracket under T minus D double dash by C. According to the laws of reflection in dielectrics, we can say theta I is equal to theta naught and Eg is equal to tau multiplied by E of I, and Et is equal to 1 plus tau whole multiplied by Ei, where tau is the reflection coefficient for ground and theta I is equal to grazing incidence. The received signal contains two types of components: LOS ray that propagates through the free space from the transmitter and reflected ray from the ground surface. The distances covered by the LOS ray and the reflected ray are presented as D of loss, that is equal to root under D square plus bracket under Ht minus Hr whole square, and for D reference, that is equal to root under D square plus Ht plus Hr whole square. Depending on the phase difference phi among the LOS ray and the reflected ray, the received signal may experience constructive or destructive interference, that is phi is equal to 2 pi bracket under D ref minus D loss by lambda, where lambda is the wavelength of the radiating wave that can be calculated from the transmission frequency. Now, under large-scale assumption, the power of the received signal can be expressed like this, where the decay is 40 dB per second for path loss. And with this, we have come to an end of this session. Let's take a quick recap on the salient points. And today we have learned introduction to ground reflection or two-ray model, requirement of this model over free space propagation model, line of sight and reflective parameters of this model, equation for calculating power of a received signal with this model. We will meet again with another interesting topic of wireless communication. Till then, keep watching and keep learning. Bye.